Right, so I passed out two things to you guys. One of them is this like daily lesson thing. You know how last year I gave you guys, well, Eric doesn't, but last year I gave you guys note guides, like skeleton notes. I'm doing the same thing this year, but in this case, what I handed out to you was all of our first unit. Okay, so I'm not just going to do like note guide at a time. You're getting kind of everything at once. Okay, and when we're done with the first unit, I'll give you all the second unit, and so on and so on. Okay, the second packet of papers I gave you are practice exams. Okay, it says practice for the BC test, so we're going to be using those this year too. You can keep them in one binder. If you want separate binders, one for notes, one for practice exam, that's okay. However you want to organize it, all right? Okay, so this is your cover page for your notes. You can put that in your binder wherever you want to. The next page, if you flip it, is the table of contents. So I'm trying to get more organized this year, okay, now that I kind of know how this class operates, because this is the third year for the course. It's fairly new, so I'm trying to get more organized as the years go on. We're going to accumulate all of our note guides, so I think that this is a good resource for you guys to have after the class is done. You'll know exactly kind of what's on what page as we go through. If you take a look at this table of contents, we only have 4 units to cover. That's less than half of what we did last year. Okay, so in terms of the BC exam, about 60% of the BC exam is AB material, meaning what you did last year. The other 40-ish% is what we're going to cover this year. Okay, so we're going to have a lot of AB review this year just to keep it fresh. Okay, and then the last unit, I call it a unit, but it's not really a unit. We have a bunch more practice exams that we're going to cover towards the end of the year. Okay? Let's go ahead and flip the page. All right. So this is what I call the cover page for our first unit. On the left-hand side, you'll see the days. This is how long I think it's going to take us to cover these particular lessons or sections. This is just a guide. It might take us more time, it might take us less, but this is just my idea. Okay? You can also anticipate when a partner quiz or test is coming up, so I think that's useful. I go in to tell you kind of what that section is about, what we'll be talking about. And the last column are the pages from this kind of note guide that we'll be working on. So the first section is about 7 pages long, and you have about 3 pages of homework. Okay? So far so good? All right. So our first section, we're going to pick up in this class where we left off last year. And if you remember, the very last topic we were talking about last year was volumes, like doing those rotations and things. Okay, so we're going to pick up with that, and that's going to transition us into our first kind of topic in BC. Okay, so if we recall from AB, what must you integrate to find volume? Any ideas? What does that little integrate symbol mean? It represents antiderivative, right, in terms of in an equation, right? But what if we're talking graphically? Antiderivative in terms of a graph represents, or the area under the curve. We have to integrate area to find volume. More specifically, we focused on the area of a circle. Do we remember the area for a circle? Okay, Cameron? Pi, and what was the second part? R squared. Perfect. All right. So if we're going to figure out the volume of an object, we're going to kind of rotate it in a circular motion around an axis, and in that circular motion we're going to integrate the area of a circle, pi r squared. Okay, so we have two different ways we might rotate an object or some type of graph. We can rotate it around a horizontal axis. Okay, maybe we're going this way. But you can also rotate it along a vertical axis. Maybe we're going that way. And depending which way you're rotating it, we have to be careful in terms of the variables that we're using. If you're rotating it around the horizontal, aka x-axis, you want to make sure you have x variables within your integral. If you're rotating it around the vertical axis, aka y-axis, you want to have y variables in your integral. Do you remember this from last year, how we may have had to rewrite an equation to make it fit? Okay, that's the whole idea here. So for horizontal axis, we want our equation to look like y equals something, but for our vertical axis, we want it to be x equals something, because this would be in terms of x, and this would be in terms of that y. Okay? So we're going to take a look at some examples that might come back to you guys, and we'll just see how these go. Okay? So let's take a look at the first one. Find the volume of the solid formed by rotating the region bounded by these graphs around the x-axis. Let's go ahead and draw a picture first, just so we have a visual of what's going on. Can we draw a square root graph? Basic square root graph? Remember what it looks like? Where it starts? Go ahead, Caitlin. Yep, I like that sideways parabola. Yep, definitely. All right, and then we have x equals 1, which would be a vertical line at the value of 1. So we want the region bounded by these two graphs and the x-axis. So if we were to shade in that region, that would be this guy. Hello. Yes!
Here's you just need it for today, right?
Yes.
Okay, because this is going to go in lab 29
Okay.
eventually, because they can't hook up to the desktops to those.
If it works.
To the board.
Well, today's the last key day, right? Until it's supposed to.
Yeah, I hope so.
I hope so too. Yeah.
Yeah.
So I'll give it a shot. If it doesn't work, I'll just give it back to you.
Okay.
Or just put it in.
No, just get it back. Yeah, I'll put it in there. They
Okay.
those are all new desktops in there, and it doesn't work with the board.
Perfect. Okay. Thank you.
Okay.
All right. So we're going to take that shaded region and we're going to rotate it. It's telling us around the x-axis. Notice how that's our horizontal axis. So let's go ahead and find our volume. If we're going to find volume, we need to integrate the area of a circle. So we have pi, and typically r, but r represents something different in this case, and squared. Since we're going around the x-axis, we need a dx on the end. How do we kind of figure out what represents that r, aka radius? What do you think? What do you think, Eric?
It's just the graph that we see superior x-axis, or its axis of rotation is x-axis, then the graph.
And the graph. Okay, so if you were, remember how we did rectangles, like left endpoint, right endpoint, midpoint, all that fun stuff? If you were to draw a rectangle from your graph down to that x-axis, I don't care if it's left endpoint, right endpoint, or whatever, this rectangle is representing the radius, okay, the length of that circle. Because if you were to take this rectangle and rotate it around that x-axis, it would form some type of disc, like a solid frisbee type shape, okay? So this distance is representing our radius. So we're going to take that distance simply by taking the top function minus the bottom function to get that distance. So we would have the square root of x, which is the top curve, minus the bottom function, but that's just the x-axis, which has a value of 0. I like how Eric kind of worded it. He said you take the equation and then you subtract the axis, if you can think about it that way. All right. What about the bounds on the integral? Can we figure that out good, Caitlin? 0 to 1. Perfect. All right, 0 to that x value of 1. Good. All right, so let's go ahead and try to figure this out. If pi is a constant, we can pull that out front if you want to do that, one of the properties for integrals. Inside those parentheses, we have the square root of x minus 0, which is just the square root of x. But notice how that's being squared. So the square root and squared would cancel each other out. We're just left with that x variable. So let's go ahead and work backwards. Antiderivative time. Can we work backwards from x? Go, Caitlin, or not Caitlin, Cameron. There we go. And we're specifically working from 0 to 1, so we can draw in that bracket and put the 1 and the 0 there. Thank you. Yeah. Thank you. All right, so where do we go from here to find the volume? How do we use our bounds? Which one do we plug in first? Go, Caitlin. Top. Okay, so plug in the top. Plug in 1. Pi times a half times 1 would just be 1/2 pi, or maybe some of you write pi over 2. That's the same thing. Top bound minus bottom bound. If we plug in 0, we'll get 0. So it looks like our volume is pi over 2, or 1/2 pi. So if you were to take that blue area, rotate it around the x-axis, you would be able to fill that solid with pi over 2 cubic units of whatever you're dealing with. Water, milk, who knows. Okay? Is it coming back to us? Maybe never left? All right, let's go ahead and check out the next one. Find the volume formed by rotating the region bounded by y equals 1, the square root of x, and x equals 0 about the line y equals 1. Let's go ahead and draw a picture. Alright, our first equation, y equals 1, we have that solid horizontal line. Our second equation is another square root. And our third equation, x equals 0, is just another name for the y-axis. So if you were to fill in or shade the region that borders all of those different equations, we would have this kind of triangular shape in there. This time, though, we're rotating it about the line y equals 1, which we already graphed. Notice how the axis of rotation is another horizontal line, right? So in terms of our volume, we need a dx. It's another horizontal line. So if we're going to find volume, we have to integrate area. Notice how we're rotating it in a circle. So we got to integrate the area of a circle. We have pi, and then we got to figure out what this radius squared is. So if you were to draw one of those rectangles within that shaded region, we have to identify kind of what the top function is or the bottom function. You could use Eric's idea of equation minus axis. That would work as well. Can we identify our top function? Okay, Caitlin?
Square root of x and then minus 1.
Okay, so you could do that. Notice how that would be the equation minus the axis. If you did top minus bottom, it would look like 1 minus the square root of x. Okay, but what actually is happening is that order doesn't particularly matter, because when you're squaring it, it would eventually kind of reorder itself and it would be exactly the same. Okay, so you do have options. I know last year we did top minus bottom. Maybe equation minus the axis is a little bit easier for you to remember. You can use either one. Okay, let's go ahead and figure out our bounds. Where does that shaded area begin? Where does it end? Good, Eric?
0 to 1.
How'd you get the 1? That's good.
Because I know that I cross that way, the square root of x equals 1, this x bar is also 1.
Right, we have to figure out what is that intersection point, aka when does the horizontal line and the square root equal each other. So if you were to set the square root equation equal to the horizontal equation, you could figure out when they're exactly the same, which would be at 1. So we're still going from 0 to 1. Let's go ahead and maybe we'll do this by hand. I know we'll get to some calculator ones in a second because you like those, but let's try this one by hand. So maybe we'll pull out the pi, and let's go ahead and expand the square root of x minus 1 squared. So if you were to write that quantity twice and go through some distribution or FOIL process, can we anticipate what that would look like? Good, Eric?
X minus 2 square root of x plus 1.
X minus 2 square root of x plus 1. Can we get that? Alright, so let's go ahead and maybe work backwards from here. Okay, none of those are like terms, so we can't go any further. If we were to work backwards antiderivative from each term, we'd have 1/2 x squared. What about the square root term? Maybe you want to rewrite that as a power of 1/2 to help you out. Good, Eric?
Negative 4/3 x squared over.
Okay. We still hanging in there? Alright. And then backwards from 1 we have x. Alright. Where do you guys want to go from here? We can do a lot of different things. We could start to plug in the bounds. Maybe you want to distribute in the pi. Do we have a preference? You want to do the bounds first? Okay, let's do the bounds. Alright, plug in 1. So we have 1/2 minus 4/3 plus 1. And then we would have to subtract, plugging in 0. We still have the pi out front. You keep that with each term. If you plug in 1, you keep it. If you plug in 0, you keep it. We're doing this twice. But if we plug in 0, notice how everything's going to go away. So that's nice. One half minus 4/3 plus 1. Can we get common denominator? Simplify the fractions. Any takers? Good, Eric?
So 1/3.
I got 1/6. Let's see if we get a common denominator. This would be 3/6, 8/6, 6/6, which would be 1/6. So times pi, that would be pi/6. We're doing okay? All right. Let's go ahead and check out another one. Find the volume of the solid contained by the region bounded by the cubic function, the horizontal 8 function, and the vertical x graph about the y-axis. All right, let's draw a picture. What does a cubic graph look like? Basic cubic? X to the third? It's hard to describe. we got the little dance motions going on, right? Okay, like a little snake or S-type curve, like that, goes through the origin. We have y equals 8, so horizontal line at 8. And then x equals 0 is another way to say the y-axis. So bounded by all of those, we're looking in there. And we're specifically rotating it around the y-axis this time, which is a vertical axis. So what do we need in our volume integral? Let's see, we'd have pi, radius squared, and the last piece of our integral, dy this time. Yep, we're going around a vertical axis, aka the y-axis. Alright, so we have to figure out two things. If we have a dy integral, we got to make sure we have y's within that radius spot. And not only should the radius represent y's, but the bounds should represent the y-axis beginning and ending points as well. Okay, so what do we want to tackle first? Do we want to do the radius? Do we want to try the bounds? Say it again? Bounds. Okay, so we start at 0 and we go up to 8. Okay, and radius, you could do equation minus axis, or instead of top minus bottom, in this case, if you were to draw a rectangle, it would be horizontal, right? So instead of top minus bottom, you could do right minus left, whatever is easier for you. Okay? What do you think our radius might look like? You gotta be careful. Caitlin, you were about to.
You said be careful.
No, go ahead. See if you did it.
The cube root of y minus 8? Or is it minus...
What? Okay, so that's our equation, and then we're going to subtract the axis. What is this axis?
Oh, 0.
It's 0, right? Okay. So I like how Caitlin rearranged her equation, right? If this is a dy integral, we need an x equals equation. You got to take that cubic and bring over that power of 3. So that'd be a cubed root. Good, good, good. Let's go ahead and simplify. We could probably pull out the coefficient of pi. We would have the cubed root of y squared. Can we rewrite that as an exponent to help us with the integration process? Good, Eric?
Y to the
2/3. Perfect. We can integrate, work backwards. Y to the 2/3. What did we have previously? What did we start with? Good, Cameron? 3/5 pi to the 5/3. And our bounds, we have 8 to 0, or 0 to 8. All right, top minus bottom. So if we were to plug in 8 for that y. It doesn't really matter which exponent you perform first. You can either raise 8 to the 5th power, which would be massive, right? 8 to the 5th. Or you can take the cubed root of 8 first. Do we have a preference? Can we more easily calculate 8 to the 5th or the cubed root of 8? Which is? 2. All right, so 8 raised to the cubed root, or 1/3 power, would be 2. 2 to the 5th, because we haven't used that yet. 32, and then 32 times 3/5. Say it again. 96 over 5. All right, so that's what we get when we plug in the top bound, minus plugging in the bottom, but that's easy because that's just 0. So we have 96 pi over 5 as our volume. You doing okay? Do you guys want to try one on your own? I'll let you use a calculator on this one because it's a little involved. It's what? That's because you're seeing it for the second time, right? Any takers for the setup? Good, Eric? Cube root of y, and then minus 1. Good. Okay, after the cube root. Perfect. So we have the equation minus the axis. What about the bounds? Go ahead. 1, 2, 8. Good. Right? So we're starting at 1, and we're going to 8. Do you remember how to type this in our calculator? What buttons we press? We refresh our memory just in case we don't. Math, yep. Say it again. It is the 9th. It should be the 9th on all of them. It should be the integral option. And what's nice about if you have this kind of operating system, it pops up with the exact format that you need to type everything in. So we'll do 1/8 pi Do we know where a cube root button is?
That's what I'm trying.
You could do y to the 1/3. There is a cube root button though.
It's under math.
It's also under math. It's option 4. Oops. Now, on your paper, I know it says y, but on your calculator, you still type in that variable of x. And let's see. 9.74-ish? Does that sound about right? Yeah? I'm not sure if I typed that in right or not. You got something different?
And that's what mine is correctly.
Oh, I'm missing a parenthesis in there. Aren't I? Maybe not. No.
Are you using a calculator or readings or readings?
It shouldn't matter for this one because we're not dealing with trig, but it's in radian. Let me try something else. Math 9. I think that's what I got before. Times pi. I took the pi out initially.
You still got the same thing.
Yeah. Eric, what did you get?
I got liquid pi and I got 13.3
Let's see. All right, so volume 9.739. Okay, 3 decimal places. You could round it or truncate it, completely up to you. Did we do okay? All right, let's keep going. All right, calculator permitted again. Number 5. Find the volume of the solid that results when the region enclosed by that graph is revolved around these different lines. All right, so we're gonna have 4 different graphs. Maybe we'll draw all the graphs first, and I'll let you guys go off and set up your integrals to find your volume, okay? So our first graph, if we were to graph negative x squared plus 1, can you describe the shape of the graph? I know it says calculator permitted, so you could always graph it to get a picture, but can you anticipate in your head what it should look like before you actually graph it? Remember transformations? Yeah. Crosses at 1. All right, so a downward parabola that has been shifted up 1 unit. Good? So that's basically going to be the graph for all of these. It just depends what we're rotating around. So in part A, we're revolving that area around the x-axis. In part B, we are revolving around the y. In part C, we have the equation y equals a half. And then in part D, we have x equals a half. All right, so I know the directions can be kind of vague, especially for C and D, as to what area you're rotating, but I want you to go ahead and fill in the area that I have on the screen just so we're all doing the same piece. All right, so go ahead, try your different volume equations. You can use a calculator, see how you do. How do we do on part A? 1.676? We gotta go over any piece? No? Okay. What about part B? We're rotating it around the y-axis this time. So you gotta make sure you rewrite your equation. Could we get 1.571? Right. C and D, kind of trickier ones because you have a different axis of rotation. In part C, we're going around a horizontal line, so we need that dx. And we could write equation minus axis, which is that 1/2. What's a little tricky with this one is you had to figure out that intersection point because you're no longer going to this x-intercept. Your area is cutting off a little short. So you could have found the intersection using the graphing capabilities. You could also have plugged in 1/2 in for the y in the equation and solved for x to get that same value. But after you have the bounds, we should be able to get the volume. How do you do? Okay. Very similar process for D, but it's a vertical axis, so we need a dy. We have our equation minus axis. Again, finding intersection point, you could have done that on the calculator, or plugged in 1/2 in for x in the equation to figure out your y height and get 2.29 as the volume. Not too bad? Perfect. All right, so all of these examples that we've been doing so far are referred to as disks because if you were to draw in those rectangles at any location inside that area that you are revolving, all of those rectangles would touch that axis that you are revolving around. Okay, it's a disk. So when you're revolving a solid area, you're going to form a solid 3D figure, okay, a disk type shape. Tomorrow, we're going to get into washers. Okay, what if not all of those rectangles are flush? Okay, what if we have some space missing? So we'll see how those work. We doing okay? Perfect.